My name's James Bultitude. I'm the Chief Technology Officer here at OrbitFab, where we're building gas stations in space. I've been with OrbitFab since the very early days, joined the company in about June of 2018. My company was founded in January of 2018. And over the last 5 years, we've been building the technology and the team to execute on-orbit refueling. So quite a similar service in some ways to what our colleague at Northrop Grumman was talking about, but different in a number of fundamental ways and more tailored towards long-term architectures. You can see we've been strategically invested in by a number of companies, including Lockheed Martin and Northrop Grumman in the past. I'm going to start by just talking about what is OrbitFab. So our mission is to build the in-space propellant supply chain. So where before Northrop Grumman was speaking about specific vehicles going to specific places to fulfill specific needs, we're all about optimizing the logistics and providing a universal refueling solution for the entire industry at multiple orbits. Primarily right now, that converges down to LEO, particularly around sun-synchronous orbits, and up to GEO, where we actually keep our assets in a GEO plus, so GEO plus 300, kind of the belt between the deactive GEO belt and the graveyard orbits. The reason we do this is that we want to create a bustling in-space economy supporting permanent jobs in space. So we want to see a future where thousands of people live and work in space. And we believe that that requires a baseline of infrastructure. And that infrastructure starts with mobility, which is driven by propellant. Over time, it goes into resupply of commodities for space stations, all kinds of things like that, and eventually becoming a petrochemical company, if you will. Obviously, they're not petrochemicals for space. What's happened so far at OrbitFab? So we're headquartered in Lafayette, Colorado. It's about halfway between Boulder and Denver. And we have an office in the United Kingdom. That office in the United Kingdom is located at Harwell and is scaling up. We're 60 plus employees growing globally, probably far more than 75, 80 people now when you include full-time contractors and things like that as well. We've flown 2 successful spaceflight missions. You can see quick images of them, but we'll talk a little bit about them in more detail. One to the ISS with these 2 free-flying vehicles that you can see here with astronaut Christina Koch, which we launched in 2019, very early in the history of the company. And then another one, the spacecraft Tenzing, which we launched in 2021. Tenzing's a 35-kilogram spacecraft that's the world's first orbital propellant depot. It's really a logistics demonstration for us of how do we get a dangerous propellant into a spacecraft, get it into space, fly the interfaces, move that spacecraft around, image things, and really learn about what we need to do in order to support more and bigger depots in the future. The other big thing that we do is we sell what we call the Rafty service valve, which is the industry standard interface for refueling. We've seen fantastic adoption and spent 5 years improving and continue to improve that interface. It's designed to be a drop-in replacement for a fill drain valve, as well as an in-space refueling interface that enables docking. We'll talk more about that as well. So what kinds of vehicles do we build? How does this all kind of fit into the ecosystem? So we build 2 principal vehicles at OrbitFab, shuttles and depots. A shuttle vehicle is a capable vehicle that has rendezvous proc stops and docking capability, that's able to fly up to a Rafty and fiducial equipped client and put fuel into them. It's then able to fly over to a depot, which is a simpler vehicle that contains a lot of fuel and a Rafty, and grab fuel to return that to other clients. So it's with this architecture of 2 basic vehicles that we're able to fulfill the needs. Now we have to place those as noted in LEO, GEO, and we're starting to look at how we get them into cislunar as well, based on kind of customer demand there. We are not satellite servicing vehicles and don't see ourselves as satellite servicing vehicles. When we look at the work that Northrop Grumman does or Astroscale's Lexi does, those satellite servicing vehicles that are designed to dock with an unprepared client, we like to think of them as tow trucks, if you will. We're a gas station, not a tow truck. And so we would pass fuel to those vehicles in a number of instances for them to be able to more optimally fulfill their operations. And we would do that via one of our shuttles. We would top them up so that they can potentially do multiple life extensions. We actually have a contract with Astroscale to do such a thing in GEO in around 2028. I alluded before for the 2 big things that we really do as a business is sell this Rafty service valve. We don't sell it at a high price. We sell it at a fair price in order to make it the open standard within the industry. We manufacture it. We offer it up under an open license, which effectively means that we're not holding on to the design and technology on that forever. We want to make sure that we ensure quality as with any standard, and so we're taking our time to get the licensing right there. But that will be an open standard for the license for the industry. Sorry. That we're going to talk to in more detail. And then obviously we sell fuel, primarily right now, hydrazine and xenon. But really the sky is the limit with respect to fuels. It's a matter of what order they come onto the technology pipeline based on customer demand. Why refuel? So we heard a little bit before about mission extension, and mission extension is a reason to refuel, but in a lot of ways, to me, it's not the most exciting. The most exciting is when you think about how refueling can enable a next level of mobility unheard of in the current way we design space missions. The other thing that it can enable is flexibility. And so at the moment, when we start designing a spacecraft, we plan every operation for the spacecraft's life from the beginning. And if we want to plan for flexibility, we have to plan that flexibility in, which is not really flexibility. It's just, you know, over planning. Refueling enables you to take an asset that's performing well in space and choose to do new things with it, which is super exciting. It also enables in a hostile environment, which unfortunately we see more and more of in space, for you to outmaneuver a potential foe. If someone is harassing you, it enables you to kind of like reinforce your position. But most excitingly to me, it enables new operations and business models that we haven't conceived of. I like to think that we're building an internet in a lot of ways, and I'm not going to try to project forward what Amazon is or anything at this point in time. I'm excited to see how people take unlimited mobility in space and apply that to their problem set. When we talk about costs, this slide breaks out a number of the ways that we save money for people, why you would fiscally want to refuel. Primarily, you can launch with a smaller fuel tank. You can do fewer satellite replacement cycles and get that cost benefit above. But also you can realize revenue benefits from refueling. So you can take the revenue that you were going to be generating on orbit and add to it. And that's where we see mission extension and retasking and those kinds of things. So both cost benefits and revenue benefits. Let's talk about Rafty. I'm an engineer. It's always fun to talk about the technology. So Rafty, as you can see, is this piece of equipment on the left-hand side. It's a completely passive interface for a spacecraft. So that means that when you plummet into the spacecraft, these AN fittings come off and it gets welded in. You don't need to attach it up to any electronics. The only thing electrical on it is these heaters. It's all actuated by springs. There's a number of seals in here that meet 91.710 requirements. There's passive covers in here that when the active side comes and grabs onto it, the covers are retracted. And the reason we've done that is we wanted to make the client-side interaction as simple as possible and as reliable as possible. That allows us to take the complexities and put them into the mechanism side that lives on the shuttle. That allows us to do good assessment on that over the course of its life and really understand when to retire those assets. It also allows us to upgrade grip over time. So while Rafty can be kind of like a finished, finalized product earlier, grip can get better and better with more evolutions. Yeah, so I think the right approach to the problem is to simplify the client interface, which we place on spacecraft clients to be refueled and on our depots, and put the complexity in the shuttles. Rafty exists, and it's not huge. It's around the same size, weight, power, and cost as 2 fill drain valves that you'd be putting on a spacecraft traditionally right now. You can see that it actually has 2 valve cores, and then wrapped around those is a grapple fixture and a cover assembly. It sticks out a little bit, and basically these V-grooves on the side are what allows us to be docked with it. You want to use it in concert with fiducials. We have some exciting fiducial technology at Orbit Fab that we'll be releasing more about in the future that allow for, lots of different lighting conditions for you to still be able to dock with the spacecraft. There's some dimensions here. And on the Rafty side, I'd really, for anyone that hasn't checked it out before, point people towards the Rafty Users Guide that you can go to our website and download. It's a large document, and it really doesn't just encompass Rafty, it encompasses how to make your spacecraft reusable. It'll be followed up with a refueling operator's guide, which if you're a spacecraft operator or a mission planner, that's kind of the manual on how to do a refueling operation in space. So yeah, that's part of the work that we're doing here as well, is to make sure that along with the physical hardware and the standards work we do with Confers and other organizations, that the documentation is out there for people so that they can start thinking and designing from the beginning. how am I doing on time? All right. I'm going to talk about a couple missions we've flown and we're flying in Orbit Fab.
We
and
still
then,
have 15 minutes, James.
cool. So when we founded in 2018, one of the core kind of things we backed our business with was this ability to fly early and fly often and learn from that as much as possible. And so I joined full-time in June of 2018, and by October of that year, we were actually launching our first payload to the International Space Station. The second half of it launched in 2019. So it was a rapid program. We learned a lot. So with these two vehicles here, you see what we call a rigid tanker vehicle and a flexible tanker vehicle. At the time, we were investigating flexible fuel tank technologies. We're still super interested in those for long term. If you think about it, long term, if you're grabbing propellant from the moon or somewhere like that, do you need it to survive launch loads? Not really. So it doesn't really need to be in a big spacecraft tank. It could be in a bag like this. But what it also allowed us to do is test the plumbing topology. So how we place our pumps, valves, those kinds of things to allow for us to be able to grab fuel and give fuel from our vehicles. At the end of that, we hit an exciting milestone for us on the business side, which was we were the first private company to supply water to the ISS. So there was around 4 gallons of water that we launched up to the International Space Station, and we didn't want that water to go to waste because reusability is important to us. So that got pumped into the ISS water supply for the astronauts to drink and use. From there, we spent a lot of time working on our interface Rafty. And in 2021, we decided that Rafty was ready for flight and that we were ready to learn how to build an entire spacecraft in-house, working with a bus manufacturer, but really coordinating the whole effort. So we built and launched this 35-kilogram spacecraft containing 90% high-test peroxide to an SSO orbit. You can see it deploying here from Transporter 10 on this Sherpa vehicle with support of Spaceflight, our launch integrator there. It was also a really rapid program, 9 months from ATP to launch, and really enabled a lot of learnings. We fueled high-test peroxide twice on this program at the Cape Canaveral Space Force Station over Rafty, once here, once for our refueling system that's in here, and once for this Benchmark Space Systems Halcyon thruster. What's next? So at the moment, we have an IRAD program where we're looking at de-risking rendezvous proxops and docking. So how do we fly spacecraft in close proximity? As a previous colleague, the kind of from Northrop Grumman alluded to, these are complex situations that need to be done right. And so Podracer is an everything but docking RPO demo mission where we launch, we fly in concert with a client, get up really close, and then back route. And it enables us to really test the safety at every level of the system. So we can go in and we can fly to our first hold point, do an abort, look at the performance. Really look at how we abort, look at how we move in space, and test the physical operations and not just the simulation on the ground. So yeah, we're excited that spacecraft is brokered for launch on a Transporter 10, so January of 2024, another rapid program. Excited, and I personally spend most of my time these days working on this mission, while at the same time the rest of the team, most of the team are working away on Rafty, improving grip, and working on the deliverables of fuel that we have for government customers in GEO. We're excited to be able to announce that the government is a customer and that they have lent in, the United States government, and that they will be buying propellant from us. Not an R&D mission, not a demonstration, but they are buying propellant from us, which is super exciting. We're able to show that we can sell a commercial service to the DoD, which for people that have been close to that kind of procurement market for a while, that's an important milestone that we all need to see in government procurement. Yeah, and with that as well, we have another program where we're providing a bunch of equipment, and so we anticipate in 2025 doing 2 refueling operations for the United States Department of Defense in GEO, more as a depot than as a shuttle there. And so when we take that and the work we're doing on RPO, we put that together and we get to our shuttle product that is really what our commercial customers need to see in LEO and in GEO in order to really get fuel into them quickly and easily. As I alluded to, we have a number of commercial contracts as well, as I mentioned, with Astroscale to refuel that Lexi vehicle, that life extension vehicle, for 1,000 kilograms of fuel in GEO. And we have a partnership with ClearSpace, making debris removal spacecraft refuelable, which really enables better debris removal. I heard in the comments a lot of discussion about debris removal and LEO, and this is a good step towards that. We do a lot of work on that at Orbit Fab. It's a major market for us. When you go to remove debris in orbit, it's not just no one's going to be able to remove all the debris, but every piece of debris you remove makes a significant difference. As we heard as well, the Kessler syndrome, I truly believe, has already begun. It's not a huge explosive single event. It's a slow rise. And so what we're seeing now is that there is an increase in the levels of debris that does not match the increase in the levels of launch activity. So it is a runaway effect already. That said, it's not, you know, a huge explosion, but it is already runaway. And so it is something that needs to be addressed. So working with ClearSpace, we're able to bring the cost of that refueling activity down to a much lower point than you can see in other refueling activities that aren't using refueling. And the UK Space Agency has been a really strong backer of that kind of work. And that's why we have an office in the UK and are building up our footprint there. NASA recently released a study that we were pleased to see where they examined different ways to do deorbit work. It came out like last week, and a lot of our work had flowed into that, and we're super excited by that. Yeah, that's pretty much everything I have with respect to slides. I wanted to leave as much time for questions as possible. Yeah, happy to answer any questions.
Perfect. So thank you, James, and it's good to see again that a company with this vision of sustainability is doing so well, and you know, congrats on the government contracts as well. And again, we all happy that that's really happening, and very innovative again company and great team. And you know, I know some of your colleagues as well, and I'm staying tuned again on the LinkedIn and you know other social media. Really, you know, leading there also on the forefront as well as a company. So I think that's really important. Okay, so now moving into some of the questions. Obviously, I have some of those for you as well.
Mm-hmm.
So let's see, the first question could be, so can you discuss the potential benefits and drawbacks of using a centralized refueling infrastructure versus a distributed approach, for example, where multiple refueling depots are deployed across the orbital environment?
Yeah, so we're definitely not centralized. I would say we're universal, not centralized. So the orbital mechanics doesn't allow you to build one depot to rule them all. When you see the art of our really large stacks of depots, in some ways that's art. You know, those are 6,000 kilograms. And in geo, it does actually make sense to put together collections of 6,000 kilograms of propellant. But you're still going to have multiples. So in geo, I anticipate a good architecture is 3 depots, all at plus 300 kilometers, which means that they're processing around the arc. And really in geo, it's about the time, right? Because it's the time you're going to take to get out of your orbit to process, to do the operation, either a shuttle coming down or a client coming up. At first, I think a client coming up is the better approach. Eventually, shuttle coming down is a good approach to match what's available from Northrop Grumman's in terms of that kind of like always on capability. But yeah, in LEO, it's going to have to be a distributed architecture. So when we do work with constellations, we recently did an analysis for a major constellation. We looked at effectively filling an entire Falcon 9 with depots that are independent free flying vehicles. And really the goal there is then to make those vehicles as simple as possible. So they're really, you know, fuel bottles with very basic buses attached to them. All they really have to do is hold their kind of like position and pointing. And it's more about pointing stability than pointing accuracy. And then you have a number of those shuttles on there as well. And those shuttles are able to basically hop between those depots and clients, grabbing enough fuel to do a refueling, doing a refueling, hopping to the next one, and sometimes affecting plane changes as well. The cool thing there is that becomes a race against time, because if you have hundreds of assets that you want to refuel within 1 year to enable them to live longer and then deorbit or retask their constellation or something like that, it's all about doing it quickly, right? And the doing it quickly thing gets exciting because that's kind of the debris problem, right? If we wanted to go and deorbit, say, the Iridium constellation, because there's a lot of satellites there and they could long-term generate a lot of debris once they're at end of life, right? I'm not trying to throw, you know, just an example of a constellation. You have to do it quickly, right? If you do one a year and you launch a new deorbit vehicle every year for 25 years, that's not going to be an effective deorbit service. But if you're able to accomplish hundreds of these operations through this disaggregated, but universally compatible network, it's really quite powerful.
Perfect, wonderful. So thank you for that. And my next question is, how does Orbit Fab ensure the safety and reliability of its spacecraft refueling operations, particularly if we're talking about the, let's say, the potential risks such as fuel leaks and contamination?
Yeah. The short answer is through robust engineering practices and really caring a lot about this, right? It's always a balancing act between moving quickly and doing demonstration missions and getting the perfect system that has no risk, right? And so for each program that we participate in, there's a different balance, right? Some of our IRAD problems, it's really about doing no harm to other people and less about maybe getting our own success criteria. Meanwhile, some of our other missions for DoD, right? Like it's really about having no failures. We use traditional systems engineering techniques. We bring in a lot of external reviewers. We lean on big space people. We lean on NASA people, DoD people, international colleagues, to really make sure that everything that we do goes through massive amounts of review, and is really well understood what the risks are, and how we're going to address them. And then with respect to like the docking stuff, which is one of the major places of risk, we spend a lot of time on designing for passively safe trajectories. So 99% of the operations we do in space are passively safe, meaning we're in this natural motion circumnavigation, where if the spacecraft die, they're going to drift apart. And then at the last minute, you kind of move into this area of risk. With respect to contamination and propellants and those kinds of things, I mean, Rafty has 3 separate inhibits with like 5 seals. It has closeout covers. When you see two valves next to each other, that's not for a biprop, that's for a propellant and a pressurant. When we do biprop, separate rafties in separate locations. I actually think biprop is going to go away in a refueling future, because if you can refuel, the 20% performance increase that you get from biprop is quickly replaced by just having a single commodity and refueling more often. So.
Perfect. And how does that work? Because that's one of the other questions that I have. I wanted to ask that to the Thomas Carroll as well, the previous speaker, but obviously there was no time to really ask him. So what happens in case an operation goes wrong potentially, right? So God forbid it happens, but what if again with the docking there is again happens that the spacecraft is thrown out of orbit, or then potentially leads to its collision to some other spacecraft. So who is liable for that basically, and who upon who the responsibility goes? Is it Orbit Fab that they're gonna turn to? Oh, okay, so you guys made a problem there with my satellites, and now is it that Orbit Fab now owes the company a compensation, or how does that work?
Yeah, I mean, it's a complex question, and I also think that the question is really not what happens if, but when, right? When we live in a future where there is lots of economic activity and lots of physical activity, when we have this real bustling space economy with hundreds of thousands of operations per year, at some point something will go wrong, right? We just have to look at, even highly reliable rocket launch companies, look at Soyuz, a very reliable vehicle track record on ISS. And so it's not about trying to build a future where absolutely nothing ever goes wrong. It's about building a future where the harm that happens from that is minimized and the fault is understood, right? So that negligence is kind of avoided. So I would say the system we have with the launching states being responsible for everything right now is a fairly effective system, considering the complexities of kind of international business and everything there. In the future, we may see that exercised more thoroughly, right? Like we've had collisions between pieces of debris effectively, or live spacecraft and pieces of debris. And the launching states, there happen to be 2 launching states that aren't really going to exchange money and information there with Russia and the United States, right? I anticipate that we will see the insurance markets and the insurers coming in. That's why Munich Re is an investor in us, and being able to insure these activities in space. And we'll see more governmental oversight on orbit operations. So currently, like in the US, which kind of really leads a lot of the licensing stuff, operations are really licensed for like on the ground, right? You're getting a license to get to space, and you're telling them how you're going to act in space, but there isn't oversight on how you actually act in space. So one of the things we proposed is kind of a customer score, if you will, of everyone, where everyone puts out as much information as they would like about what they're actually doing in space, not what they're going to do in space. And then they then get scored on how much information they've given out, but also how many good practices they've actually accomplished in space to prevent accidents, basically. And then how do you incentivize that scoring? Could you have a national reserve of propellant in space or something like that, and give people credits back towards things like refueling, because they say, hey, you've moved out of the way of 10 objects this year, right? So that's good activity. Go top up as a result. Yeah. There's a paper we put into International Astronautics Congress that was all about that, where we looked at kind of a donut model for space sustainability, which is a new model of kind of like what is the complete picture of space sustainability.
Perfect. And the next question from my side is obviously as a from a perspective again of a company that does refueling and docking with the spacecraft. So what do you think could be done from a perspective of designing those spacecraft initially in the first place by the operators and the manufacturers, so that satellites are more again compatible with those vehicles and refueling operations?
So I would say go download the Rafter user's guide if you're a spacecraft designer, read it and understand what's in there. Most of it comes down to CG, placing your interfaces with respect to your CG intelligently. Everyone should be flying fiducials in the future, even if you don't intend to be refueled, because it makes it easier to identify and deal with you, whether your spacecraft is alive or dead. Everyone should be flying deorbit interfaces and refueling interfaces, in my opinion, even if they're not designed into your operations at the beginning. And then really thinking about your modes of your spacecraft so that the computing is ready to deal with in orbit operations. You want to make sure that you have modes that you well understand with respect to your GNC. If you imagine two spacecraft docking together where neither of them have GNC designed for that, there could be a horrible kind of fight between them for actuator control. So you really want to make sure you understand that's well documented, and that you have ways potentially to even modify those modes in future as we learn more and more about how to design GNC modes for spacecraft docking.
And do you believe that the government should be again in charge of putting those again regulations when giving away licenses for the spacecraft to ensure the operability and standardization?
The government has a responsibility, since the government's responsible as the launching state, to make sure that people launch good spacecraft, but also operate them appropriately in orbit. I don't think that the government should be writing standards and interfaces from the start. I think they should look to good industry practices and then back up good industry practices. And so that's where I think organizations like Confers are really important, which is a kind of an industry-led group that DARPA backed, where we all get together and we talk about what are the standards that are important. And I think at first it's about standardization of language so that we can talk and act in the same way, right? And then eventually it becomes physical standards. We don't start with physical standards. We start with, what does refueling mean? What does docking mean? What does prox ops mean? That's really variable right now in industry. So, yeah.